Have you ever stopped to think about the invisible rules that make our world work? I mean, really think about it. It turns out the exact same law of physics that gets your car engine roaring is also what's keeping the food in your fridge cold. So today, we're going to dive in and uncover this incredibly powerful principle.
Okay, so here's a question that people have been wrestling with for centuries. How do we actually turn fire into motion? You burn fuel, you get heat, you make a car go, but why is there always so much wasted heat coming off of it? To really get this, we're going to have to do a little thought experiment, starting with the simplest, most bare-bones scenario you can imagine.
So, let's imagine a situation where a gas expands, but it does absolutely zero useful work. I know, it sounds a little weird, but trust me, understanding this is the key to unlocking everything else. We're talking about a thought experiment here called free expansion. So, what is free expansion? Well, it's pretty much what it sounds like. You just imagine a gas expanding into a total vacuum. There's no air, no resistance, literally nothing pushing back against it. Just pure, unchecked expansion. Okay, picture this in your head. We've got a container, right? And it's split down the middle by a piston that has no mass. On the left side, we've packed it full of gas. It's under pressure. And on the right side, nothing. A complete and perfect vacuum. Now, we're holding that piston in place, but what do you think happens the second we let go? The second we release it, bam, that piston just shoots to the other side. But here's where it gets really interesting. The piston moves so fast that the gas molecules, for just a split second, are kind of left behind. Then they all rush in to fill up the new space in this totally chaotic, jumbled mess.
And what's the result of all that chaos? Well, the gas did exactly zero useful work. Nothing. Why? Think about it. When the gas was actually pushing with force, the piston wasn't moving. And by the time the piston was flying across, the gas wasn't really pushing on it anymore. It was just expanding into empty space. So it accomplished nothing.
So this is the big puzzle, right? If just letting a gas expand on its own is completely useless for doing work, how on earth do we build these massive, powerful machines that turn that exact same expansion into motion? How do we take that chaos and actually harness it? Well, the answer is a machine that's been specifically designed to solve this problem: the heat engine. See, instead of just letting the gas fly out into a vacuum, we control it, we manage it, so we can squeeze useful work out of it. Let's break down how this brilliant device actually works. A heat engine, this is the heart of pretty much everything. Your car, power plants, you name it. Its job is, in principle, really simple. Take heat, which is just messy, disordered energy, and turn it into work, which is nice, orderly, useful motion. And here's the thing. Every single heat engine, doesn't matter how simple or complicated it is, follows these three basic steps. 1, it sucks up heat from something really hot, like burning fuel. 2, it uses that heat to expand a gas and do work, like pushing a piston. And 3, it has to dump the leftover waste heat somewhere colder, like the air around it. And you cannot skip that last step. It's non-negotiable. What we're really looking at here is a fundamental rule of energy accounting. You can't just make energy up and you can't destroy it. You can only change what form it's in. So all the heat you put in from the fuel has to be accounted for. It either becomes useful work or it gets dumped out as waste heat. It's a simple, strict budget and it governs everything. Okay, so this brings up a really cool idea. If we always have to waste some heat, what's the absolute bare minimum we could possibly get away with? What would the most efficient, the most perfect engine you could ever build? What would that even look like? So back in the 1820s, this French engineer, Carnot, was obsessed with this exact question. He came up with this purely theoretical engine cycle that would basically set the ultimate speed limit for efficiency. It's not a real engine you can build, but it's like the perfect blueprint, the gold standard that all engineers have been aiming for ever since. And this is his baby, the Carnot Cycle. So in step 1, the gas expands while it's absorbing heat, but its temperature stays the same. That's isothermal. This is where you're getting work from the heat. Then it expands even more, but this time with no heat going in or out. That's adiabatic. And that makes the gas cool way down. It's like you're getting bonus work just from the expansion itself. The last 2 steps just reverse the process, compressing the gas and kicking out waste heat to get it all ready to start over. It is, theoretically, the most efficient possible way to do this. But look, you don't need to memorize all those steps.
The absolute key takeaway from Carnot's entire genius thought experiment is this beautifully simple formula. The absolute maximum efficiency any engine can have, it only depends on two things: the temperature of the hot source and the temperature of the cold sink. That's it. The bigger that temperature gap, say between your burning fuel and the outside air, the more efficient your engine can possibly be.
Okay, so Carnot's perfect engine gets work out of a temperature difference. But what happens if we flip the whole thing on its head? What if we put work in specifically to create a temperature difference? Well, I'm willing to bet you already own a machine that does exactly that.
A refrigerator is literally just a heat engine running in reverse. Think about it. Heat naturally wants to flow from a hot place to a cold place, like water flowing downhill. A heat engine harnesses that natural flow to get work. A fridge does the total opposite. It uses work, in this case electricity, to force heat to go where it doesn't want to go, from a cold place inside the fridge to a hotter place, which is your kitchen. It's a heat pump.
And this brings us to a classic brain teaser. You're hot, it's summer, so you think, I'll just leave the refrigerator door open to cool down the room. Will it work? The answer is a definite no. In fact, it will actually make your room even hotter. But why? Remember that energy budget we talked about? So, a refrigerator's job is to pump heat from inside to outside, but with the door open, it's just grabbing heat from one part of the room and dumping it out the back, which is still in the room. But that's not all. The motor doing all that work gets hot itself, and it adds that extra heat to the room too. So you're actually adding more heat to the room than you're moving around. So all of these things we've been talking about, engines, refrigerators, waste heat, they all point to a single, profound, and totally unbreakable speed limit of the universe. It's the law that governs all of this. This is the dream, right? The ultimate goal. An engine that takes in, say, 100 joules of heat and turns it into 100 joules of pure, useful work with absolutely zero waste. Is that even possible? And the laws of physics deliver a very clear answer. No, it's impossible. Remember Carnot's efficiency formula? To get to 100% efficiency, that cold sink, the place you dump the waste heat, would have to be at absolute zero, the coldest possible temperature in the universe. And since we can never actually reach absolute zero, a perfectly efficient engine will always be out of reach. And that brings us to the grand finale, the big one, the second law of thermodynamics. It is one of the most fundamental rules of reality, and it basically says you can't break even. Every single time you convert energy from one form to another, you are guaranteed to lose some of it as low-quality waste heat. Perfection is simply not on the menu. So what's the bottom line here? We live in a universe that has an unavoidable energy tax. Perfect efficiency is a myth. And this law has huge implications for, well, everything. How do we innovate? How do we build a sustainable future, knowing that every single thing we do, every energy conversion, always comes at a cost? Now that's a question for all of us to think about.